And today we're going to talk about building energy efficiency at the time of electrification and what role passive house plays in this new scenario. So Emil, we used to be architects. We typically refer ourselves as recovering architects. I'm still registered back home, although we don't design buildings anymore. And we are the number one providers of hands-on passive house training for builders across the country. In fact, we take our passive pod workshop to different locations. We're going to talk more about that later. And we do some consulting for projects, as I was mentioning earlier, mostly as a way to support our builders in the first or second passive house project or high performance project once they have taken the training. It's also a way for us to keep our curriculum relevant and up to speed with new products or new challenges that new projects or retrofits have. So we refer to ourselves as a teaching hospital for passive house, so to speak. Uh, I honestly love teaching adults because we typically don't have to deal with the parents of our students, and we get to drink beers with our students, which is pretty nice. But also, every student that we meet, the participants to our training, they bring new questions and new challenges. And in trying to answer those questions, I find that very rewarding because it gets me to think about the same matters or new topics in a different way. So I'm really thankful I get to receive those questions because it's a way through which I personally grow and we grow our training with that. And now I would like you to pop in the chat. Who are you? So raise your hand or actually type the number in the chat if you work in construction and you are an architect or designer, please type 1 in the chat. And if you are a builder or a contractor, please type 2. Just to get an idea, this is just for fun to see who we have in the crowd here. If you have some specialty work in construction, if you're a product rep, an engineer, HVAC installer, MEP, Windows, please pop 3. And if you work with permitting, inspections, testing, number 4, or something else, but still in construction, please type 5. And if you don't work in construction and you're here because you're here by mistake and you are regretting it, please type 6. If you want to improve your own house, please type 7. And if you don't work in construction, but you have a general interest in green building, please type 8 in the chat. Cool. So I see a good mix of answers. Very good. Thank you for doing that. It's nice to meet you all. It's good to have an idea about who we're talking to. And it's typical for us to get a mixture of different backgrounds. And that is, I find that very inspiring because with more diverse backgrounds, we get more questions and more different opinions and answers. So it's a better conversation as opposed to being very monocolor and not very diverse. So what is new in construction these days? If you have been following the news in construction, you have probably heard a lot about embodied carbon. You may have heard about healthy materials. There's new courses and new research done in materials and toxicity and how that impacts human health, as well as electrification. Electrification is bringing not just buildings, but also vehicles and other industries towards the one vector of electricity. And today we're going to talk more about electrification. What is electrification? I just mentioned that cars are becoming electric. Your heating system may be becoming electric, as well as your cooking or your domestic hot water. And so why do we care about electrification? Any idea, any thoughts about that? In teaching, I've learned the value of open-ended questions. And one of the main reasons why we care about electrification is because if we electrify our buildings, our vehicles, then we can use renewable energy and move away from fossil fuels. So that is one of the main reasons why there's so much push towards electrification, not just in construction, but also in cooking, in cars, and other sectors of our lives. So raise your hand or actually put an X or whatever in the chat if you own a heat pump. Do you own a heat pump? Please put an X or raise your hand in the chat. Let me see, we have questions. We have a few. Cool. So for those who has answered no, do you own a fridge? Because a fridge is a heat pump. And we make this analogy just to remove some of the fear around heat pumps that a lot of builders as well as owners have about this new technology, which is actually not new. If you think of a fridge has a compressor that steals heat from inside the fridge and dumps it to the back of the fridge. And that phenomenon is called the heat pump. So when we have buildings, we have a device similar to the fridge, so a compressor that takes heat from the exterior air when it is heating season and dumps it to the inside to provide heating. And we care about that. So if you look at the left side of the slide, that is an air source heat pump, which does what I just described. So takes the heat from the exterior air and provides that in form of heating to the building. On the top right of the slide, we have a ground source heat pump that does something similar where it takes the heat from the ground and brings it to the inside of the building. Just air source versus ground source heat pump. On the right-hand side of the slide, we see a heat pump water heater that takes heat from inside the room to generate domestic hot water. So all of these are heat pumps in the electrification process that we are talking about. Now, why do we care about heat pumps? And why does this slide read, why are heat pumps efficient? Do you know why? The reason is that it's a good deal in terms of the exchange that we have with the heat pump. For every unit of energy that you provide to the heat pump, it provides you with 2 to 4 units of energy back. So imagine you give $1 to Joe, and Joe gives you $2, $3, or $4 back for the $1. It's a good deal. So it's a very efficient system because it provides you with more energy than what you supply it with. And that energy comes from the exterior air for an air source heat pump, comes from the ground for a ground source heat pump, or comes from the room the heat pump is installed in the case of the air source, of the heat pump water heater. So that is important. That's going to come up later. But typically, we like heat pumps because they are more efficient than a regular electric heater, where that deal is a one-to-one unit of energy. So if you have an electric heater, just your electric baseboard, for example, you gave it 1 unit of energy, and it gives that back as a 1 unit of energy back. Whereas a heat pump, it is a 1 to 2, 1 to 3 or 4 exchange. So it's a good deal. Now, keep in mind where that energy is coming from for heating. In mild climate zone like Boston, for example, an air source heat pump is most cost effective because the exterior air does not get super cold. Whereas we were chatting about my house up in the mountains in Colorado at 8,800 feet of elevation. There are several days when it drops below 0. So the exterior air is not very rich in heat, so it's very cold. So I am considering doing a ground source heat pump because the ground is at a more constant temperature. Now, the convenience of one or the other, air source versus ground source, really depends on how much energy you use in a year. If we're talking about very high performance buildings, such as passive houses, for a single family home in climate zone 4 or 5, air source heat pumps are going to be most cost effective as opposed to larger buildings like a school or a hospital. That is probably more convenient to do a ground source heat pump just because you use a lot more energy. And that is also to be accounted for if you're using the same heat pump to generate heating as well as domestic hot water. That becomes, the more efficient your building envelope becomes, the more the domestic hot water is important in the overall energy balance of your building. We're going to talk more about that later. So why are they so efficient? If you look at this graph, this is the performance you get from the same heat pump in producing heating versus producing cooling. A lot of heat pumps can produce both heating and cooling, but most of heat pumps, in fact, all of heat pumps are more efficient in producing cooling than they are at producing heating. So just looking at prioritizing your effort, it's always important to not neglect the efficiency of the building envelope, so the level of insulation, air sealing, and windows, because even if we switch to heat pumps, they are not that efficient in producing heating. They are more efficient in producing cooling. So that is something to keep in mind. This graph specifically shows an average, not super efficient heat pump, but if you look at the HSPF, is the BTUs that you get in heating for every watt hour that you of electricity you give to that heat pump, and it reads about 8.8 or 9. And for cooling, that efficiency is almost twice as much. So for the same watt hour that you give to that heat pump in electricity, you get about twice as many BTUs for cooling. So it's a much better deal for cooling. So this leads us, if you want to have a holistic approach to how the building performs, when we switch to heat pumps, it's still very important to give high importance to how we insulate the building, how we air seal the building, and the level of efficiency for windows and doors, because heat pumps are much better at producing cooling than they are to produce heating. Now, in life, I really care about the time of the day you run your toaster. That is a joke, but it's also not a joke, because in using renewables, then the time of the day we use energy does become more sensitive. And this cartoonish picture shows the same house in wintertime, clearly the right-hand side of the picture, and the summertime on the left-hand side of the picture. And in prioritizing our strategy for a building, we want to keep in mind that a heat pump in the summertime produces energy, most of the cooling during the day, whereas in wintertime, that need for heating is mostly happens at night. This seems obvious, and I hope it is, but it's very important to keep in mind the strategy, because if you're trying to offset your energy in trying to get to net zero, this is an all-electric scenario, your heat pump producing cooling is working during the day at the same time that your PV system is producing electricity, which is a very convenient deal. Whereas in the wintertime, your heat pump has to work, it's less efficient because producing heating is less efficient than producing cooling. And it produces that at night. There is no sun at night. So if you have PVs on your roof, then they are not active at night. So in trying to be smart at getting to net zero, you want to factor this in, because if you don't do that, then you end up using a lot of electricity from the grid, and the grid is very carbon intensive across the country. So you may have the perception of doing an awesome job because now you have switched to a heat pump, but you're actually drawing a lot more electricity during the night, during wintertime, and you're getting a lot more coal-intensive electricity from your grid. So playing more on that, I put together a couple of examples based in Denver, but it's a pretty similar climate. It's clearly more dry, but temperature-wise is similar to Boston. This is an example of a house, new construction. This is actually a passive house. I'm just using this as an example of a new construction. If this is built to the latest energy code instead of passive house, the heating load is about 60,000 BTU per hour. And to cover that in a typical year, with a gas furnace will be about $900 to $1,000 in Denver with Denver energy prices. Whereas with a heat pump, it's about $600 or $700 a year. So you save some money just switching from natural gas to a heat pump. In a retrofit, this is actually a project where we're doing a passive house retrofit, but we're using that as an example of just an existing building, your 1980s house, with zero improvement to the envelope. If you're just switching to a heat pump, your heating load is about 250,000 BTUs per hour. Your heating that with the gas furnace is about $2,800 to $3,000 a year. Whereas with a heat pump, that drops about, you save about $1,000 a year because of the deal, because the heat pump is more efficient. So this is in a normal scenario, climate zone 5, Denver, new construction built to the regular 2021 energy code, as opposed to the existing building from the 80s without any improvement to the windows, no additional insulation, just as is, switching from a gas furnace to heat pump. Now, the problem is it's much bigger when you have extreme weather events. In Denver this year, we had a polar vortex where for 84 consecutive hours, Denver was below zero. And for those of you that are not familiar with Denver, that very rarely happens. You know, it's pretty sunny. It may drop down to 10 degrees, but to have 84 consecutive hours, that's pretty extreme. And so that put a lot of heat pump out of order. So one of the issues with heat pumps is that this is an air source heat pumps that we're talking about. It takes heat from the exterior air. And if that exterior air is too cold, then that heat pump cannot work. Now, there are some cold climate heat pumps, and you want to be very cautious about selecting a good one because there's also a lot of supposedly cold climate heat pumps that are very not high performance. So they shut off or they become very inefficient. And when they shut off, the alternative is to have either a furnace, a regular furnace backup, which is probably most cost effective, or as we're showing in this case, having a full electric backup. So just a big ass electric resistance in your ductwork to heat up that air instead of the heat pump. And if you do that for a new house, over just 84 hours, it's going to be about $200 or $300 of extra electricity bills because an electric resistance is very inefficient. And if for a regular house, 1980s, no improvement on windows or insulation or anything, if you're switching to electric resistance heating, over 84 hours only, it can be $1,000 of additional energy bill. So this is something that you want to be very cautious about because if you're switching to all electric, you want to make sure that your heat pump actually can endure cold temperatures. Otherwise, you're exposing yourself to being either out of heating or having very, very expensive energy bills. This is just to put some cautions in your action moving towards all electric. Then what is next in construction? We talked about electrification, we talked about healthy buildings, we talked about embodied carbon. And actually what I see next in the context of construction is this guy trying to sell us electric cars. We are living in one economy with one grid and one market. So the fact that electric vehicles are becoming more and more popular is something that is going to impact the construction industry as much as other sectors. And we care about that because there's going to be one energy bill, and this is going to be our lives in the next 5 to 10 years. So how does an EV compare to a house in terms of energy consumption? Have you ever tried to ask that or find that out? By the way, in the newest and latest definition of net zero building, the charging of electric vehicles at home does fall under the umbrella of the energy that you have to offset for your building to be called a net zero building. So in moving forward, if your city requires buildings to be net zero, it is on the horizon for that net zero balance to also include charging of electric vehicles. So that is something we need to keep in mind, because it's coming. It may be 5 years out, but this is the direction the whole market is going. So we looked at the new house, 2021 code compliant to the left, and the regular house without any improvements. And we did a breakdown for the as is, and you see on the left-hand side, the new build, where 2/3 of the energy, the solid orange, is actually the heating. The 3.9%, the dashed white and yellow line, that is the additional heating due to the the heat pump water heater. That is the water heater that takes the heat from inside the room. And that heat comes from somewhere, and that comes from the heating system. So this is a line of cautions for anyone installing a heat pump water heater. That heating is coming from your heating system. That heat pump water heater becomes just an extension of your heating system. If your existing heating system is not that efficient, your energy bill is going to go up. Then looking at the breakdown, about 1% is active cooling, about 6 to 7% is domestic hot water, and then about 20% is appliances, home appliances for the new construction. And then on the right-hand side, we have a similar breakdown, but because it's an existing home, about 75 to 80% is actually heating. Now, if we look at these are just percentages. If we look at the actual numbers, this is what it looks like. So an existing house requires a lot more heating than a new house. Although you'd be surprised how much less energy you can avoid by actually doing much better than code minimum. We're going to talk about that later. Now, what happens when we start adding 2 electric vehicles per house? Elon here comes to our door and tries to sell us electric cars. Now, that energy bill goes up significantly. So this is something that we want to keep in mind because this is coming, it's maybe 5 years out, but this is the direction the whole market is going. And so how much PVs can you install on your site, either on your roof or in your garden, if your goal or if you are required to get to net zero? So there is a limit in how much we can offset the energy that we consume at home once we start accounting for electric vehicles on top of buildings. So this is something that we want to keep in mind in advising our clients. Now, how much better or how much more efficient can we make electric vehicles or buildings compared to what is the minimum requirement today? Have you ever asked yourself that? So I looked into today's EVs, and I tried to look into tomorrow's EVs, and I didn't find much information about how the technology can be better. I'm not talking about batteries. I'm not talking about how much longer the range can be. I'm talking about how many miles can we get from a kilowatt hour. At the end of the day, with EVs, we are moving tons of steel, and that is not efficient to begin with. So unless we start building cars out of carbon fiber or something that does not weigh 2 tons, then I don't see a ton of improvement in the mileage that we get from EVs. But I also did not find much data as far as what is coming next. There's a lot of focus on batteries, but little less as far as miles per kilowatt hour. Now, for buildings, for new construction compared to the baseline code, you can reduce the overall site energy demand by over 50% by switching to passive house. This is not just heating and cooling, this is for the overall. And for the existing building stock, this is actually our project being retrofitted as an NFIT. That can be up to 60% plus. Again, this 55 and 60% is looking at the total site energy demand for domestic hot water, appliances, heating, cooling, and electric vehicles. Once you switch that, then once you implement passive house or NFIT, then you can save up to 50 or 60% compared to the regular building stock. And one note that came from the Intergovernmental Panel for Climate Change for the construction industry, this is back from the conference in China in 2019, is that the construction industry has dramatically higher potential for improvement compared to other sectors, including transportation and food production. So it's really key for our development as a society that we make buildings better, not just by switching to PVs and heat pumps, but to make them better insulated, better airtight, and with better windows and doors. That is one of the biggest potentials that we have as the construction industry. Now, we talked about heating being the biggest part for both the new construction and the existing buildings. Where do you think the greatest areas for heat losses are in a building? And this is where I'd like you to type in the chat, so please pay attention. If you believe that exterior walls are the greatest source of heat losses in buildings, please type 1. If you believe that the ceiling of the roof or the roof are the greatest area for heat loss of the building, please type 2. Yes, of course, there are considerations about, is it a two-story building? Is it a ranch? Don't care. If you believe that the walls are the greatest, type 1. If you believe the ceilings and roof are the greatest area of heat losses, please type 2. Air leakage, if you believe that that is the greatest area of loss, please type 3. Windows and exterior doors, please type 4. Doggy doors, please type 5. I am not judging. We have many clients that want to have efficient doggy doors. We can talk about that. And we can talk about unrealistic expectations. Or slab and losses through the ground, please type 6. This is the choice. You can type different numbers if you'd like. But this is where I try to get the sense. So we get some, let me see. Air leakage seems to be popular. Doggy door doesn't seem to be. If you saw a doggy door, you would type 5 in a heartbeat. Mail slot. I would use that in the next one. Thank you, Steve. Good. Thank you for the feedback. We can talk more about that in a second. And I don't know, because I don't know which buildings we're talking about. So to answer that question, we developed a study, which is available for free download. There's a QR code at the end of this presentation if you're interested, where we looked at 50 different single-family projects across different climate zones to answer the question and many other questions. And these are single-family home new construction. And if you're building those projects, 50 of them, to comply with the 2021 Energy Code, then the number one area of heat losses is windows and exterior doors, by far. Over a third, more than 1/3 of the heat losses in average over 50 projects in different climate zones, it's exterior doors and windows, excluding air leaks. We're going to see what that means in just a sec. Second one is exterior walls. Third is losses through the ground to the outside air. And fourth, all of the air leakage combined of the building. So this is something that in trying to promote building science, we developed this research. We're going to see a QR code at the end where you can download the report. But in trying to prioritize where to put the effort, clearly air sealing your building is a low-hanging fruit and it is important, but it only addresses about 10% of the air leaks in your building. 1/3 is exterior doors and windows. We're going to see more about that. And then something that blows people's mind is heat losses to the ground. So towards the end of this presentation, we show, but it's available on YouTube. So if you go to YouTube and type EMU Passive, the latest video we published is about heat losses to the ground. And that is one of the areas that is mostly disregarded from construction professionals across the country. So please go check out the video, because this is the kind of science we're trying to bring to the market. Again, windows, exterior walls, losses through the ground, either with your slab or with your basement walls. Again, this is the average over 50 different projects. Some of them had basement, some of them did not. Some of them had a conditioned crawl space, some of them had unconditioned crawl spaces. It's a mixture. These were 50 actual projects. And I'm happy to answer more questions about this later. But statistically speaking, the heat losses through the ground cause more losses than air leakage. And this comes as a piece of mind-blowing information to a lot of builders today. Now, that being said, if you compare this breakdown to the breakdown that we have if those 50 projects were to the passive house level, the breakdown is actually pretty similar. Number one is still windows. Number two is still exterior walls. Number three is still heat losses to the ground. And then so on and so forth. The difference is that the absolute amounts are much less in passive house because we insulate more, we air seal more, and we have much better windows and doors. But that breakdown is still the same, and the losses through exterior windows and doors is still number one. Now, how does passive house compare to other energy codes? This is one of the outcomes that we worked on for that report. So if you're wondering, how does passive house compare to EnergyStar, or how does passive house compare to the zero energy ready home or the regular building code? This is the reduction of site energy for heating and cooling combined for all different building standards compared to if that building is built to the 2018 energy code. This is the average for all 50 projects that we modeled, and we modeled them for each of these building standards. And you can see that if you switch from the 2018 energy code to the 2021 energy code, which is the gray and white dash box column on the top left, from the 2018 code to the 2021 code, you save about 9% of heating and cooling combined. Now, something that I found very disappointing is that we modeled also the draft of the 2024 energy code that had not been released yet. And that is actually worse than the 2021 code. So we can see that the regular energy code is kind of stalling, is not really improving much. In fact, the 2024 energy code is slightly less efficient or produces slightly less efficient buildings than the 2021 energy code. The California 2024 is kind of its own thing because it's only California projects. You see the EnergyStar reduces the need for heating and cooling by about 20%, 26% for the Department of Energy Zero Energy Ready Home. Pretty Good House is about 40%. And then you see the Phius and PHI low energy building around 50 to 55%. And the International Passive House Standard, PHI Passive House, reduces about 70% in average the need for heating and cooling compared to the 2018 energy code. If you have more questions about this, we can get into the chat, but this is kind of an overview of what these higher performance standards can bring to individual projects. Now, back to the breakdown, we saw that over a third of all of the losses were to the windows. So ask yourself, in a new, well-installed high-performance window, where do you see the greatest heat losses? Wait and type in the chat. Type 1 if you think the greatest heat losses are at the head of the window. Type 2 if you think it's at the jamb. Type 3 if it is at the sill. 4 if you think that the greatest heat losses are through the glass. 5 if you think that the greatest losses are at the glass edge, meaning the connection between the glass and the window frame. Or 6 if the greatest heat losses are through the window frame. Or 7 if you think that it's air leaks. This is a new well-installed high-performance window? Please type in your numbers and we can chat. So I see, let me see. I see some sixes, so window frame. I see some glass. I see some five. Okay, good, good. Awesome. I see a seven. Awesome. And uh, I see, okay, more seven. Cool. Thank you for that. That is always good to have this chat. And we took a high performance window and we modeled it. And we also included the testing result for the air leakage. And this is what we found. So if you read the pie chart with me, the bluest wedge is the big dark blue at the bottom, which is losses through the frame, just conduction losses to the frame. And this is a high performance window with a triple pane. And it's actually, you see the cutout, you see the window frame has insulation inserts inside the frame. And even though it has insulation inserts and the frame is only on the sides, there are more heat losses through the frame of the window than we have through the glass, which is the light blue color there. Then, number 3 is the dark brown, which is the thermal bridging between the window frame and the wall. We're going to see a little bit more about that. The third one is thermal bridging again between between the frame and the glass itself. Then the air leakage, the total air leakage is around 2% of the total heat losses. I'm going to say it again. In a high performance, well-installed window, the heat losses through air leakage is only about 2% of the total heat losses. I'm saying that because in conversation we have over and over with our builders, there's an equation in the mind of builders, window equals air leaks. And everything else is disregarded. So this is, if you look at it in the context of everything else, air leaks is actually only 2% of the total heat losses. This is very important because it drives your conversation about which product to select. So this is a window install detail at the head. I wanted to have it large so you can see some details. You can see it's the same window, so you see the insulation inserts. This is installed on a wall with about 4 inches exterior insulation. So you see in this detail, the exterior is on the left-hand side and the interior is on the right-hand side. You see the drywall, you see the darker gray is cellulose insulation, the kind of brown is the headers, then you have your sheeting, and then you have the exterior mineral wool insulation. And this is a high performance install where the window is in the middle of the wall. There's another video on our YouTube channel that talks about positioning the window in the wall thickness and why the performance of the window is best in the middle of the wall, because in this condition, which is optimized, the heat losses of the thermal bridging, which is the dark brown wedge on the left-hand side, count for about 14%. So 1 in 6 losses through that window are just because of the install detail. This is just, it's not about poor install, it's just the way that the detail is designed and executed for the insulation. You also notice that we have insulation extending over the exterior of the frame of the window. The reason for that is once we start looking at the heat flow, you see there's a lot of bypass effect around the frame, and the frame is one of the areas with greatest heat losses. So we want to add some additional R value over that frame. This is a way to make your windows perform better, and performing better means having higher comfort as well as being more energy efficient. So conduction through glass, conduction through the frame. Let me see here. This is the thermal bridging at the glass edge that I referenced on the left-hand side. Then we have the thermal bridging at the window-to-wall connection. This is very big. That is why we want to have that additional insulation over the window frame. Then we have air leaks at the window itself. In this case, it's an operable tilt and turn window. So the leaks happens between the sash and the frame of the window. And then air leaks at the connection between the window and the wall. So this is all based on lab and field data. But to give you a context of how much air leaks matter as opposed to just having a good window matter. Because there's a lot of conversation on the internet about air sealing windows, but the window that you are air sealing is actually pretty low performance. So you're still getting a pretty low comfort level, or even though you air seal very well, that window is very poor performing. So you're going to have a very uncomfortable building in the first place, which leads me to asking, why do we care about windows? I kind of gave it away. But, this is what we get. This is a brewery in Colorado that effectively lost business because how uncomfortable it was. I love beer. That was my beer glass, and I could not sit next to that 39-degree temperature window pane because it was so incredibly cold. So they effectively lost the sale of at least 2 beers because I had to leave because it was so uncomfortable. And that is normal, as it is normal to have ice forming on the inside of the glass. This is my office in the house I used to live before in the Denver area. And one day I was just working at my desk and I had ice forming in front of me. This is a building that is less than 10 years old. And as a naive person in the 21st century, what I did was post a picture of this on the internet. And I got, on LinkedIn, I got so much shit from fenestration professionals, people that work every day in making windows. They assume that the ice is absolutely normal. And I'm like, maybe we speak a different language. In my world, we should not have ice forming on the inside of the windows. And so if you're thinking about what building codes deliver, that is not comfort. These buildings depicted here comply with local energy codes. So if you're thinking energy codes as a way to deliver thermally comfortable buildings, this is not it. As it is not it indoor air quality. So this is a picture from the same report looking at thermal comfort analysis. You see the orange dots are buildings modeled with the PHI passive house, so the international passive house standard, and the darker blue is Phius, the American standard, which are all designed around the same thermal comfort target of having a temperature differential of less than 7.6 degrees. Whereas the code minimums, the white circles with the thick gray line, those are for buildings complying with the latest 2024 energy code. And you see how disconnected energy code is from any thermal comfort. This is just looking at window requirements over the average of those 50 projects and the average internal temperatures that you get if you stick to those code minimum window package. So this is something that I'm happy to talk more about this. If you're trying to convince your clients to choose higher performance windows, they don't care about energy. They don't care about U values. They don't care about passive solar gains. They care about comfort. Way to talk about windows is thermal comfort. And show them this picture of the ice forming inside the window. Show them this picture with the infrared camera and the story about me not wanting to have more beer. People care about comfort, and windows are a key component to delivering that. And the energy code is failing miserably at delivering that. Now, does the cost follow performance? For my house, I priced out 20 different window manufacturers, and this is what is mapped here. The picture of the window is irrelevant because most of the products that I priced out for my house were wood frame windows. And in this graph, you see the cost per square foot of windows at the bottom. So the left-hand side is cheaper, the right-hand side is more expensive. And then vertically, you see the average temperature that I get at my house up in the mountains. And you see that the most expensive one was about $285 per square foot, and it's pretty low performance. In fact, this is part of an article I'm publishing for the Green Building Advisor, where I'm going to dive a bit more deep into this data. But cost does not always follow performance. And this is, even though a window is triple glazed, typically means very little, because they may have a very low performing triple glaze. You may pay the premium for it, but you don't get the performance, you don't get the comfort. So this is an area where you want to be cautious about, because just saying that it's triple glazed is not enough. And most mainstream manufacturers, they have triple glaze, but it's very low performing, to the point that their double pane glass performs better than the triple pane glass. But they sell you the triple pane glass, and if you don't know, you're paying the premium, think that you're going to get a better performance, and you don't. So something to keep in mind and to be cautious about. Why do we care about buildings? Taking a step back, we talked so much about windows, but also we talked about buildings. Why do we care? One of my favorite quotations is from this picture. See if it comes up. How much time do you think we spend inside buildings? It's about 90% plus of our lives that we spend inside buildings. So the quality of buildings that we live in has a direct impact on our well-being and health. This quotation is from Rem Koolhaas, that in the 70s came up with the concept of voluntary prisoners of architecture. If you think about that, there is no law that forces us to stay in our homes. But our homes are not necessarily healthy or comfortable, so we are voluntary prisoners inside these man-made boxes. Now, we talked about the discomfort, we talked about mold. This picture here shows the outcome of a partial energy retrofit. What you're looking at, the black stuff, is mold, and the building as was had no mold. Then they replaced windows, they air sealed some, but they did not add continuous fresh air ventilation, so the building filled up with mold. That's a more efficient building that is significantly less healthy. Why do we care about buildings? Because we spend most of our lives inside buildings. So it makes no sense in my mind to have buildings that are more energy efficient and are less healthy. This graph on the left-hand side is kind of convoluted. It's my personal struggle try to maintain the indoor air quality, looking at CO2 concentration to a decent level. Decent level of indoor air quality looking at CO2 is if you have less than 1,000 parts per million, your indoor air quality is decent or good. And if you're above that, then you have poor indoor air quality. And this is a building that I used to live in, and it's brand new, less than 10 years old. And to get fresh air, I had to manually open windows, meaning that I had to trade off thermal comfort, the room would get cold, to get higher indoor air quality, looking at just CO2. But then my particular matter, so the pollution would also come in with the exterior air. So it was a struggle. It's a way to show that unless you think about indoor air quality from the get-go, if it is an afterthought, it's going to be a struggle to deliver that, because that needs to be addressed from the beginning of the project with a continuous fresh air ventilation system. Now, this is a question that I love asking people in class because it tells us a lot about the industry. How long does a family stay in a house they just moved into before they move out again? New family goes into a new house. How long do you think they're going to stay in that house? How many years before they move out again? Please type it in the chat. Let me see. I see some 4, some 7. Awesome. Anyone else? 15. Okay. 7. Okay, cool. So this is me asking, is it 7 years? Is it 25 years? Is it 5 years? Is it years are just numbers? So how long have you lived in the house you live in right now? Please type it in the chat. Plan for 3 ended up at 10, 13, 13, 4, 9, 30. Awesome. Less than 1. Okay. Me, 2. Awesome. So look, this is data. We want to see data. So for NHB, National Association of Home Builders, that doesn't give a crap about building better, the average nationally is 13 years. It has been 13 years for the past 10 consecutive years. If you think that the average is 7 years or 5 years, you're thinking of the market before the 2008 bust, which was 16 years ago. Now, in advising your clients and making recommendations, it's key to have this in mind. People are in average going to stay in that house for 13 years or longer because of the interest rates now are so high. Nobody's going to move out that quickly. So this is key in trying to have a context to advise your clients with. This is building science. It's not about where to put the air barrier, where to put the insulation, blah, blah, blah. That is a hobby. Knowing how long people are going to stay in a building is key to advising them properly. So, speeding up a little bit, what's the most cost-effective way to build a new energy-efficient house? So what we recommend is to use a performance-based approach, whichever the energy goal, and then do an energy analysis early on in the designs, typically the schematic design, because that helps you navigate priorities based on your climate, based on your project, and make decisions with the handrail of data to know what you're doing. As part of the same study that we're going to have a QR code at the end here, we compared a performance-based building standard, the PHI low energy building, and a prescriptive standard, the Phius 2021 core prescriptive. So we basically compared a performance-based path and a prescriptive path for a project that would get within 20% of each other for the energy performance. So we looked at, I want to get to about the same energy performance. One path is prescriptive and the other path is performance-based. What we found is that including the cost of the energy analysis, the performance-based approach was about $5,000 cheaper than the prescriptive one, because you could eliminate a lot of insulation that the prescriptive path was just requiring you to do. Prescriptive, at the end of the day, is when you know the answer before you ask the question. Whichever the prescriptive standard, Phius, code, whatever, they don't know about your project. They don't know if you have a south-facing window, if you have 2 stories, 1 story. They just come up with numbers. How? I don't know. But that has nothing to do with your project. So what we found is that if you have a performance-based approach like the low-energy building standard in this case, it ends up being cheaper to get to the same energy performance, including the cost of the energy analysis. Plus, if you have some goals to reduce your carbon footprint, what we found is that in average, the performance-based approach will get to the same energy performance with about 800 cubic feet of insulation less. It's a truckload. If you're trying to minimize the amount of embodied carbon that you're using, if you need 800 cubic feet of material less, that's a win. It's also saving you a lot of money. So this is also covered in the report. There's a QR code for that at the end. But it was a very informative because our market is based on many decisions that are prescriptive. Oh, there's a checklist, I'm going to follow that without really questioning where the information comes from. For the retrofit, on the other hand, our recommendation is start off with an energy audit and then prioritize the building envelope, because that is the way to prioritize health and comfort as well as energy savings. And then if you can, do a step-by-step retrofit, meaning that, hey, your roof need to be, I literally had this conversation with a client yesterday. Their roof was leaky, so they had to do something at the roof anyway. This is the time to build that roof to a passive house or NFIT level, with the proper air barrier, with the proper insulation level, having the vision of the whole building, how it's going to work together. And then windows and walls, they're not going to do it now. They're going to do it 5 or 10 years down the line. And then prioritize things that need to be fixed. But once you get to fixing them, just do it right and keep that overall end goal in mind. Keeping that end goal in mind keeps you from having issues like this where the existing building had no mold and they did a partial retrofit and the building filled up with mold because they were not controlling moisture properly. So with all of this, where do we land? This is the site energy for, average for all building standards that we considered. And what we found is that it takes the same amount of energy to build and operate a new house with the 2018 code, or to have a passive house and charge 2 electric vehicles at home. So looking at 5 years from now, 10 years from now, the market is going to be very different, but investing in the efficiency of the building envelope today is the way to move forward and keep our buildings to be up to speed with the times. Want to learn more? This is the QR code if you want to download the report. There's also a ton of videos on YouTube for this report specifically. If you're interested in our training, this is a QR code. We are going to be in Boston in May. So please reach out. We have a hands-on workshop in Boston coming up, which I'm pretty excited about. And then if you don't know where to start, we have a free info session every first Thursday of the month online. This is the QR code for the Zoom link. It's free. You can come in and ask any questions. It could be about training, it could be about project, and hopefully we can provide you with some guidance on where to start. Thank you so much, and I'm happy to answer some questions now.
Thanks a lot, Enrico. I have a million questions. And just, I appreciate the questions that you're asking when you're thinking about what you do for a living, because they're things that I never thought about. So quickly in the chat, there was a couple questions. On the slide with the bar charts for the window heat loss slide, Austin had asked if that was an average across all climate zones. So you did. You had the 50 study sites.
So yes, the pie chart where the windows were then that was an average across all projects. Yes. Keep in mind that please keep in mind, something I did not say, that we intentionally selected 50 projects to be enough to be statistically significant. And we selected those 50 projects from the project we work on regularly. Half of them are in climate zone 4 and 5. So New York, Boston, Denver, Chicago. A quarter of them are in warmer climate zones. A lot of them were in California. Some of them were in Florida, Texas. And the other quarter were in climate zone 6 and 7, so cold climate zones. So there was kind of a balancing selection to not skew the results too much in one direction or the other.
Okay. And then on the same slide, Josh had said that there was only a 1% improvement on windows and doors, despite the often reduced count and improved thermal performance of Phius projects windows. That was a bit surprising to him.
Well, that is for the percentage over the passive house breakdown. I'm going to pull this up. This is not Phius. This is for the international standard, but I'm going to pull up this slide so I'm going to show you because there was actually
Josh, feel free to unmute yourself too.
You're good.
So let me see here. If you can see the slide right now, the pie chart on the right-hand side is the percentages for the total losses in a passive house. If you want to compare to the passive house to code, is the graph in the middle. You see that the green part of the graph is the losses to the windows. This does not account for the passive solar gains, by the way. It's just heat losses. But you see that going from code minimum windows in the column chart to the passive house windows, the passive house windows losses are less than half than the one in the code build. So if you want to compare losses, the graph in the middle.
Yeah, I'm just surprised that the percentages didn't change more, because oftentimes windows are an R3 or an R2.5 or an R2, and then you go to a performance house certified windows. The complete unit is like R7.5, R8, right? And you would think that the mix, the distribution of the percentages would be greater because of that wild swing, the doubling of the R factor.
Yep. I was surprised myself. I was like, oh wow, the absolute numbers. So the column chart is a lot lower, but the breakdown percentages is very different. So it's very similar. So about a third of the whole losses are through the windows. What is not shown here for the passive house part is the passive solar gains. These are just losses. We did not show here the passive solar gains that you get through windows. And in fact, in passive house projects in cold climates, we see typically a 2-to-1, about twice as much the passive solar gains through passive house windows than we have losses through passive house windows. So windows become solar collectors in a way.
And that's due to a higher solar heat gain coefficient and orientation and glazing ratios and things like that?
Not necessarily. This is same building, built to code versus built to passive house. Same window,
Gotcha.
Same deal. But passive house windows have about 3 times less losses because you go from an R3 to an R7 or 8 or 9, you know.
But they're typically letting in more solar heat gain, though, as well.
Correct. In fact, one of the reasons for that is a cheap way out for a code minimum window manufacturer to improve the performance of the window is just to add a low E coating on the glass, which if you're not careful, it also limits the amount of passive solar gains you get. And there is a habit in the industry, in the window industry, to default to low gains glass because that gets you better UVAG. But you lose all of the passive solar gains, you know. So this is something that unless you do an energy analysis, you don't know. So we work with many different passive house window manufacturers, and they don't know because they don't have the handle on the energy analysis. So they default to low gains glass. You know, that muscle memory is still there. And 12 out of 10, the passive solar gains that we specify is incorrect the first time we reviewed that quote. So we had to insist on getting high gains glass in those projects that run in heating dominated climates.
Gotcha. We had one more question in the chat, which was on the window detail slide that you had.
Yep.
And someone was wondering what the kind of mid-tone brown color directly above the window frame head was. Well, I'm assuming it's like a spacer.
My awesome drawing was not clear enough. I'm gonna pull up the slide and it's gonna show it. But, you know, that is a screenshot from our energy window energy analysis. So I'm gonna try to find it. And
it was in that space that it was in that space that would usually be the gap between the frame and the jamb.
Yep. Let me share my screen. And this is the amazing screenshot. You're talking about this gap?
Yes.
So that is molded as spray foam. We typically recommend to fill that gap with insulation. No preference for spray foam, just the texture. This texture here is spray foam, but it's not an air seal. We always specify some sort of tape here to air seal to actually in this detail, the air barrier of the wall is the exterior sheeting, so here. So we typically seal at the rough opening, and then we seal back here so that we do the air seal on the four sides on the inside. We fill the cavity with insulation on the four sides, and then we do the flashing on the outside on three sides, the head and the jamb, and we leave the bottom open for drainage, but we always fill this gap with insulation, and we always have a continuous air seal on the inside. So long answer to say that is insulation in between.
So that was interesting because I was trying to understand the thermal bridging at window to wall connection. Where that was the window to wall connection, I was trying to understand where that thermal bridging was happening, if that was spray foam.
Thermal bridging is a fun thing. And I've been doing this type of analysis for 12 years. And thermal bridging is whenever you have different R values, like you have your glass R value, you have your frame R value. Whenever you have a connection of two different R values, there is some thermal bridging here. This is very evident here for the glass. You see the little arrows. Oh, let's jump into the glass, and then I'm going to bypass the high performance space. I'm going to bypass the cavity and jumping it to the outside like this. And we're kind of screwed because our way to build glass units doesn't ever solve that. And vacuum glass units, which I'm not addressed in this presentation, but we're doing research on, is even worse. So this is kind of that bypass effect at the glass. Now for the wall to window connection, at the end of the day, we have a certain level of beefiness, pass me the term here, say 10 inches, whatever that is. And we have a certain level of beefiness here, say 4 inches. And if I think of my isotherms, I don't have an isotherm image here, but the isotherms are the lines with the same temperature. So inside is warm. So my isotherms look like this. And then outside is cold. So my isotherms look like this. And at the end of the day, the isotherms of the wall need to connect to the cousins isotherms of the frame and the cousins isotherms of the glass, right? Because that is what we're doing. And the more of a bottleneck effect that you have, the more you constrain this, the more thermal bridge you have anyway. Does that make sense as a big picture?
Yeah, I think what I'm hearing you say is that the narrower that width, the less overall effectiveness and practical like insulation you have between those because of the space.
Correct. So looking at the typical nail flange install, I'm going to do a very awesome sketch here. I love Zoom. I miss my time as a kid with crayons and colors, so I abuse of that right now. But look at the same isotherms. You have the outside, you have the inside. These are nail flange install. Your isotherms go all the way down here, and on the outside they go all the way like this. And this becomes super weak from a thermal standpoint. My heat is like, oh God, I have a very easy way out. That is one of the main reasons why we have the install typically in the middle of the wall insulation. In this wall, we have some R value on the inside of the framing and some R value on the outside. That is why in trying to have the isotherms have as easy and straight path as we can, that is why we center the window in the middle of the insulation. Make sense?
On the EMU YouTube channel, there's at least one good video showing the isotherms and the different thicknesses of exterior insulation, straightening out those isotherms. Yeah. It's a good. I didn't know anything about that before. Never thought about it, and it was a good visual demonstration of what you're trying to achieve and how to think about it.
Yeah,
without being in an isotherm software.
Yeah, we don't necessarily recommend learning therm and whatnot, just looking at these best practices as a way to move forward, because the same wall and the same window, if you push your window all the way out with a nail flange installed, you lose a lot of performance, but you have paid that money. So if you're going to a higher performance level with your window package and with your wall package, which you probably need for your comfort and your indoor quality, then you want to also look at better ways to install a window and how to optimize that package.
Mm-hmm.
Cool. Well, thank you all for being over time too. We can take a couple more questions if you have any. I don't want to keep you too long. I can talk about Windows for days, so it's more up to you how long. I also need to pick up my daughter at daycare, so I have a cutoff time. But any more questions about what we talked about today? Hey, Dana, how are you doing?
Go ahead, Dana.
Hi, Enrico. Hi, it's Dana. So I have a question. My question really comes to, I'm an architect, and a lot of the work that I end up doing ends up being, because of interest rates, because no one's moving, I do a lot of renovations, and fairly large scale renovations. And in many cases, when a person is doing that scale of a renovation, it ends up becoming a conversation of, okay, well, how far do we push your envelope improvements? And I'm interested in terms of I've definitely done sort of step-by-step retrofits, and I'm always incredibly nervous when we're doing something like that. And I say, we're working on the walls, but not the roof, or we're working on the roof, but not the walls, with the idea that at some point in the future it will be done. In that interim, when it's not done, there is an incredibly weak spot in the intersection between what we're doing that's good and new and what we're doing that's bad and old.
Yep.
And I get very nervous about that. And I'm wondering, A, is that correct that I'm nervous about that? And B, what are some solutions?
That's a great question. Thank you, Dana. Some of this kind of depends on the type of project. Are you also in Boston, or where are you located?
Yeah, I'm in Boston. I'm in the Boston area.
Oh. So humid climate, fairly cold. So more exposed to risk for mold than Denver, where I'm at. Just weather-wise and climate-wise. One thing that I recommend doing is doing a as-is blower door test to see where you land for air leakage. And something I learned, I never thought about that, doing a pressurization test, because if you have a lot of dust or coal dust, I don't know, I was talking with someone from Pittsburgh, and they had a building with a lot of coal dust in the walls, and they had negative pressure, which pulled out a lot of coal dust, which you do not want to do. So positive pressure blower door test, just to get, you don't need to get a super finite number, just to know, are we at 10 air changes per hour? Are we at 15? And yep.
Yeah.
So that is also in combination with it's part of a more thorough inspection, because that I'm an architect myself, so just knowing what you're working with to begin with is very important.
Yeah.
Then really in your climate, issues may start to show up for mold and condensation if you start having around 4 ACH 50 or 3.
Okay.
So something to have in the conversation with your client, like, hey, the more we are working on the envelope, the more we need to keep this in mind. Unfortunately, I don't have a way to say, oh, if you're only doing your walls, you're going to drop to 5.27 ACH.
Right.
There's no way to do that. But you can have a look and see, hey, your walls have plaster, or if it is a brownstone building or whatever, but your crawl space is completely open. So you can guess that a lot of air leaks happens at the crawl space, It kind of depends on what you're working with.
Yeah.
So if you're fixing the crawl space, you may be losing a lot of that air leakage, which is good on one side, but that is the unplanned, uncontrolled ventilation that takes away that moisture, So keep that in mind for the conversation with your clients, because at some point you have to say, hey, we need to plan for a continuous ventilation system. Otherwise, we're going to have an issue with mold. and that kind of depends on what you're working with. That project that I showed you retrofit of, the builder is doing, it's a DIY builder doing his own NFit on his own house, living in it. So like he's one of my personal heroes, but he has not touched the Peter. He has not touched the lid yet. So basically that building is super tight at the bottom, but the lid is open. Like it's not raining inside, but it's not sealed. And the handshake agreement I have with him is like, next spring, when you start moving, working on the roof, ERV is part of that package, So it's very good thing to have in mind. The other side is thermal bridging. If you have the three big monsters are metals, concrete, and masonry. And if you have those penetrating your building insulation from the inside to the outside, that is a red flag. And maybe not a red flag. It is a red flag to be always, but it may not be an issue yet if your building is not airtight yet. The more airtight it becomes, the more your relative humidity goes up. So keeping an eye on relative humidity is part of that. If you can, finding those thermal bridges, metal, concrete, and masonry are the first thing. I never care about wood. Like wood to me is difficult to air seal, but from a isotherm thermal bridging perspective, I can sleep at night with a lot of wood penetrating my insulation. Like I sleep very well at night. Metal, concrete, and masonry are the three sources of problem. Does that make sense as a big picture?
Yeah, it does. Thank you. I appreciate it.
Cool.
Is there any benefit to working your way from the bottom up in that scenario and using natural stack effect to your advantage, that air is going to be moving from low to high?
Possibly, but really my recommendation for step-by-step retrofit is looking at what needs to be addressed today. If your windows are broken, that element is dead. You need to replace. That is the most cost-effective time to.
Yeah, if you have bulk water issues, fix those first. Yeah,
correct. Yeah, or if you have, if you got a big hailstorm, your siding may be broken. That is the most cost-effective time to air seal those walls, to add exterior insulation. That is just life happens and makes some decisions for you in terms of retrofits. And retrofit in this context have a leg up compared to new construction because in a new build you do need windows, you do need the roof, you do need your walls. Whereas in a remodel you can selectively replace the windows, but you have a roof assuming that is working and whatnot.
Awesome. Anything else? Awesome.
Well,
thank you, Enrico. This was
here.
Yeah.
Thank you so much for having me. I'm going to be in Boston in May. Again, we have a training. I'm going to share with you the information about the social event, and if you have more information, so if you want more information about training or building science, you can find us on YouTube. You can find us at Emu Passive. Somebody's asking about the QR code, which I'm pulling up right now.
I also screen captured that, Josh, so I'll send that out to our email list as well. Perfect. The QR codes.
And this is it again. Let me see. Cool. If you want to take a screenshot of that or a picture, but thank you all so much, and I hope we see each other in person in Boston in May.
Yeah, let's touch base when you're out here. Thanks, Enrico.
Have a good day.
Bye now.